thank you very much for this nice invitation. And today I'll be talking about some of the core of supernova neutrinos and how we can see maybe potentially some new physics with it, with neutrino standard interactions. And if there is time, maybe I'll just mention how we can detect low energy atmospheric neutrinos to be in the range of the NEV neutrinos. So basically, this is the outline. I will start by talking why studying astrophysical neutrinos is crucial, which I think here it should be pretty clear in this institute. And then how we can use core crop supernovae new physics probes. And I will introduce GSNV to motivate the low energy atmospheric neutrino search measurement. And then I will summarize. Okay, so let me start by showing this plot where we have different sources of basically mostly astrophysical neutrinos. And we can see that this plot spans over almost, 20 decades in the energy or so. And we see different sources, which some of them we already detected. So here we can see the parts that has been detected in the pink violet color. And of course, those detections help us to understand some of the astrophysics of how the sources are working in terms of the solar neutrinos or how the atmospheric neutrinos are created. But also it helps us to advance, of course, the particle physics, like the solar neutrino and atmospheric neutrino detection told us that neutrinos are oscillating as they travel toward us. In this plot, we don't directly see the supernova neutrinos from supernova 1978, but it also should fall in this kind of pinkish to the white region. So in order to learn more, maybe about particle physics or extend our knowledge about the sources, we would want to see all this range. But of course, some parts here are very challenging, like for example, the high energy part. Even though the cross sections for the interactions are increasing, the flux is decreasing, so it's very hard to measure that part. And again, on the low energy end, so the neutrinos that were producing the first second of the universe, or some of the neutrinos that are producing the thermal processes in the sun or in the stars, they have very low energies, even though the number of fluxes are high. And detection of low energy neutrinos, especially this energies, is very, very challenging. However, we also have this gap here in the middle where exactly the diffuse supernova neutrino background falls. The supernova neutrinos also and the atmospheric neutrinos. So hopefully with the next coming detectors online, we can close that gap and maybe learn some new physics or physics about the sources. So if we want to summarize what would be the benefits to looking for these astrophysical neutrinos, we have 25 decades in energy. We have good track records of neutrino discoveries, again, the solar neutrinos, the 1987A, the atmospheric neutrinos. We also can test physics in the conditions that are not accessible here on the Earth, like slow nuclear fusion, not really easy to do, or very, very long baselines like 1987A. But we can also use it as complement to the terrestrial neutrino experiments. If we see something, we can then build maybe or look in that parameter space better. So it's always a twofold thing. Like one is to the physics of the sources or astrophysics of the sources advancement that we're hoping to get. But in principle, because we are accessing very experimentally at the Earth challenging regions of the parameter space, for like densities, temperatures, and so on, it is also nice to test particle physics and maybe some new particle physics. Okay, so since I'll be talking about the 1987A neutrinos, of course, I have to show this picture. So I hope everyone here is familiar with it. We have just on the left-hand side, single star. It's not very different from the other stars that we see. And of course, on the right-hand side, it's a very spectacular supernova explosions, which we see in the photons. What you don't see right away, of course, here, is that hours before actually this very nice optical explosion was seen, the bunch of neutrinos was emitted from the core of that collapsing star. So even though until now we are still learning some stuff about this progenitor from electromagnetic observations, like that it's most likely that neutron star was a remnant, and people figure out also that it was most likely a binary star system, with 1978 being the heavier star. The most crucial pieces of information we actually learned from observation of this handful of neutrinos across 3 different detectors at the Earth. So here on the left-hand side, you can see the time of the arrival of different energy of neutrinos in each of the detectors. And this observation told us that basically 99% of the binding energy of the star that is collapsing is emitted in the form neutrinos in the period of approximately 10 seconds. And this is the confirmation that the star, in order to see this explosion, we have collapse of the core and then the shockwave formation, which releases later on the photons. But what was also interesting that at the time, this observation of the neutrinos allowed people to set the best limits on the absolute neutrino mass. So it was, again, the astral benefit, but also maybe particle benefit. So now, of course, we are moving towards more and more precise measurements of neutrinos. People, I think, now understand that neutrinos are oscillating between different flavors. We know that neutrinos can be described by this mixing matrix here, which have different mass states and flavor states are the ones that interact. And people have measured this mixing angles, which are quite large, and also the mass splittings between the different mass states, as you can see here. But there are still remaining questions which need to be answered, like are neutrino Majorana or Dirac particles like all the rest? What is the absolute mass of neutrinos? What is the mechanism that gives neutrino mass? What is the degree of charge parity violation in the neutrino sector? And what is the other BSM connection that gives neutrinos this masses and the mixing? So there is stuff to be done. And of course, now when we are moving towards having very nice and big neutrino detectors together with the ones that we already have, like Juno is already operational since last year. In hopefully 2 years, there will be Hypercamionande. 2 years later, Dune, maybe large Darwin detector for neutrino purposes too. And of course, the ice cube that is already existing. If we can use this to observe as many of those neutrino fluxes that we saw with better precision, or maybe close some of the windows, hopefully we can get superb sensitivity to learn more about those fluxes and the nature of them, but also maybe we can get some hints about the non-standard physics. So now I move on to the neutrinos from the quark collapse supernovae. I don't know how many you heard, but I will just give the standard view why the neutrinos are important for quark collapse supernovae and why we think those are very good factories. So for the stars with masses approximately 8 times 10 times of our sun, as they evolve toward the ends of their lifetime, they fuse heavier and heavier elements. And we end up with this onion shell structure inside of them, where the heavier elements are then dragged to the core. And once this core grows to a substantial size, meaning that it grows to the Chandrasekhar mass, and its gravitational pull can no longer be pushed by the electron degeneracy pressure, it will start collapsing. And in this collapse process, a lot of neutrinos is being produced, mostly by the electron captures on mostly nuclei present there, but also some thermal processes. And those neutrinos can be seen in the detectors of the Earth, regardless what's going to be the history of our supernova explosion. If there is a shock wave, we of course, when it goes out of the star, we can see the photons and expect the neutron star as a remnant. But in the scenarios when our collapsing core basically just ends up as a black hole, as a prompt collapse, we not necessarily see the photons, so only the neutrinos and the messengers can tell us that something is happening. In addition, we are also excited about those neutrinos because as opposed to the photons, which in order to get out of the envelope of the star, they need to interact many, many times. The neutrinos, once they diffuse or escape the core, then just travel uninterrupted. So they access very large density, very high temperature, and large degeneracies. So they can tell us not only about the outside structure, but also maybe something about the interior conditions of that collapsing star. So we can here take a little bit closer of what is happening in that collapsing core and once it bounces. So we can see different phases, would we say, of the supernova explosion. So we have the initial info phase. So as I said before, once the core starts to collapse, then we have increasing and increasing density in the core, which can, in principle, produce more and more neutrinos, which just escape readily, but they cannot escape once the density reaches around 10 to the 12, which at this point, those neutrinos are trapped by the seventh processes, so by the neutral current interactions with the large nuclei. And we can see that not fully, but if you look at this luminosity plot here, the luminosities would be increasing if we go back. And then once they become trapped, it's decreasing. The core is still collapsing more. And once the core reaches the saturation density, so the nuclei cannot be squeezed anymore, the core basically bounces back, like the inner core, which is connected, and everyone that is connected by the sound speed stops, but the outer layer doesn't know what's happening, so it hits this brick wall, and at this discontinuity, the shockwave forms, and it goes outward the shock. And as this shockwave goes outward, it will go through the layer, which we call neutrinos here, so the neutrino trapping density, and it will increase temperature very suddenly, so it will push forward the production, mostly electron neutrinos, as we can see here. And then later on, it would be just diffusion of the core that we can see in the neutrino luminosities as the newly born protoneutron star is cooling. So for some time, people also didn't fully know how this core collapse supernovae are exploding, because the shockwave, as I said, is produced at the boundary and travels upward in a pre-principle should just explode the star. It was stalling in the simulations, and it was stalling because it photodisintegrated a lot of nuclei on its way, and also there was still infalling matter on the core, so there was a large ramp pressure. But now the simulations, especially the 3D simulations, see that the neutrinos, which are still diffusing outside of the core, can inject enough energy in the stall shock to help to re-energize it, and with the help also of some hydro instabilities, this is what is exploding the star. So the so-called delayed healing neutrino mechanism. So this is the standard picture. This is the standard neutrino luminosities for different flavors and for different stars. And why, again, we think those are very good physics probes, and what we can use those neutrinos to study is, again, we access extreme conditions like 10 to the 12, that's very, very large density, and the temperatures in the core go to like 30 MeV. And of course, it's within the reach of the upcoming detector. So while with the 19H7A, we only detected a handful of the newly bar neutrinos, hopefully with the next supernovae, because we have larger detectors and detectors which can also see dune, hopefully, electron neutrino flavor, and the large dark matter detectors, all flavors. And also the super K is bigger, so also all favors neutral current there. We can learn more just to say that, okay, this is the explosion, and we get neutrinos are from 1987. We can maybe learn more about like the type of the explosion, if there is any weird quark matter in the star potentially, can tell us do more detailed models of the nucleosynthesis with the neutrino wind. It can tell us if we see it, what kind of compact object was formed, if we see sudden drop in the neutrino luminosity that could, in principle, tell us that there was a black hole formation. It can tell us something about how neutrinos are propagating, how their flavor is propagating in the environments where we not only have to worry about the forward scattering on electrons, as in the sun that is changing just their vacuum oscillation frequencies, but also the densities there are so big that they also have to worry about neutrino-neutrino standard model interactions, which gives nonlinear flavor evolution. And hopefully it can tell us something about potentially new non-standard physics in the neutrino sector, and if not, tell us we can put better constraints as always. So how we can use this supernovae as a probe of new physics? And people have thought about it already for a long time, after 1987A, of course, too. And basically, I think I split it into the two ways. We can change the diffusion time of neutrinos, or we can open a new cooling channel. So the change of the diffusion time means that we make our neutrinos scatter more or less inside a star. And in principle, that should change the duration of our signal, or maybe should change the fate of the star, because like if they cannot revive the shock, maybe it goes into the black hole. So those are the cases. Or new cooling channel. If we have neutrino conversions to the sterile particles, they should take away energy from the star and maybe again don't revive the shock. So we can put the cooling bounds in that way. But in many of those studies in the past, the astrophysical feedback was often ignored. Now I think this is moving more and more towards we should actually include that feedback in our calculations because it can change the bounds dramatically. So we will see today maybe two examples where we actually should think about the astrophysical feedback and how the bounds or predictions for some of those cases look like. So the first one would be the paper which we wrote with a lot of enthusiast people. And it will look at the lepton-number violation, neutrino self-interactions, and how that can affect the pre-bounce phase of the supernova. So why we would think about the self-interactions between the neutrinos? We are not the first to ask that question. The question about the possibility if neutrinos can interact with themselves at the strengths larger than predicted in the standard model was already asked in 1964. And at that time, Zofia was asking, do the present experimental data allow for the existence of interactions between neutrinos much stronger than their weak interaction? And at that time, the answer to this question was positive, and the interactions were allowed to be 10 to the 6 times stronger than the weak interaction. Today, this is not as large if we just think about neutrino self-interactions or the bottom-up approach. There is like 10 to the 2, maybe 10 to the 4 in some region of the parameter space that is still allowed. And again, the other motivation about the lepton-number violating part, at least for us, is that it should necessarily have a very strong impact on the evolution of the core collapse supernovae. Because maybe as you remember, when we looked at the luminosities of different neutrinos, at the beginning, it was very, very large peak of the electron neutrinos, not antineutrinos. So once we start to change that, it for sure will have some effects. So in our work, we just look at the effective Lagrangian when we can have the lepton-number violation and changing flavor, or not with the cross-section where we have mediator, which is larger than around 100 MeV. So we don't want to produce anything there on shell. So we can use just effective G-Fermi to parameterize the strength. And how we added in our kind of baby evolution of the core of the star is if we, again, take a step back, we have our neutrino trapping by this interaction, so the 7th interaction, which is the neutral current. And once those neutrinos are trapped in the core, so once this reached 10 to the 12 grams per cubic centimeters, then we can achieve the thermal and chemical equilibrium by this forward and backward reactions of protons and neutrons for neutrinos and antineutrinos for electrons. So we say that they thermalize. And now we add our lepton-number violating interaction after this happened and say that it's much faster than our weak interaction. So basically we add kind of instantaneous thermalization of their all flavors, 4 or 2 flavors once this density of trapping is reached. So how that looks in the equations, we just saw the baby Boltzmann equation, the static homogeneous isotropic one, when we have the occupation numbers for our neutrinos with the emissivity and absorption opacity. And we also track the electron fraction. So we include this charge current interactions here and there, and then the fast lepton-number violating interaction here, but it will also appear here because those rates depend on the occupation number of neutrinos, electron, and anti-electron. And then we will track the temperature and chemical potential evolution for neutrinos, antineutrinos, and electrons just by using the chain rule on this equation, when we can track the temperature by looking at the energy density and number density derivatives with respect to chemical potentials and temperatures. So this is what we will see on the next slide. Okay, so on the left-hand side, we can see the evolution of the temperature. On the right-hand side of the chemical potential of the electrons, neutrinos, and electron antineutrinos. So this is the case when we only equilibrate mu E and mu E bar Cs. And if we didn't add our L and V mu SI interaction, these plots would basically look constant up to sometime 10 to the 3, because that's the kind of strength of the weak interaction at that time. So we see once we add this L and V interaction, our temperature of neutrinos and antineutrinos come together. So the antineutrinos actually spike up and then go down, and we have the common temperature because that fluid is thermalized. Yeah, so this will be when the weak interaction finds out that neutrinos and antineutrinos distributions have changed. Yeah, so first we do the fast N and V interaction. So the temperature of neutrinos and antineutrinos changes, but becomes the same. And their chemical potentials, which were initially mu E was minus mu E bar chemical potential, also come together. So those are the same basically fluid. And then as the time is evolving and as then we come to the weak interaction, finds out that something has changed. The neutrinos and antineutrinos, they are not the same chemical potential or temperatures, then it needs to come into the equilibrium, our nu SI, with the weak interaction, and that causes this very sharp spike in the temperature because our electron fraction needs to drop down because our weak interactions want the neutrino and antineutrino chemical potential to be opposite signs, but our nu SI interactions wants them to be basically the same. So the only solution is if this chemical potential of neutrinos goes to 0, but that causes the electron chemical potential to drop down as well. So because we have much faster the nu SI than the weak interaction, we have this separation of scales, very fast interaction, and then the weak interaction. And if we look also at the evolution of the entropy, we see that the entropy changes the most once the weak interaction comes into the equilibrium. with the USI interactor. So something is happening, the entropy is going up with it should. And we can see also that this not only affects the neutrinos and electrons, it also affects the composition of our core and also its pressure support. So here we can see the proton fraction, neutron fraction, heavy nucleus fraction, and electron fraction on the left-hand side, and then the different pressure contributions on the right-hand side. So we can see that because the temperature increased and the entropy increased, now no longer we are favoring heavy nuclei. So this is just the Saha equation. And if we have very high temperature and very high entropy, we no longer want to have heavy nuclei. So that's why the heavy fraction is dropping down. We basically have now hot neutron star, which neutron fraction is going up. And also because of the weak interaction equilibration with the new SI, the electron fraction goes down. The pressure support of the core is no longer from the electrons like here it was before, but now it's actually from these hot neutrons. So we are changing basically the pressure support of the core, which can potentially also have some consequences for the evolution of that core, but for that, full simulation would need to be done to figure it out. And so that was for the neutrinos and antineutrinos in the electron flavor, but we can also do that for changing flavor. So because we saw that it's a big separation between the new SI and the weak interaction, we can now just treat all the flavor neutrinos as a single fluid, how many we want, because they should equilibrate much faster between themselves. And then the changes to the temperature and the chemical potential of that neutrino fluid can be just expressed as the sum of the changes for our different flavors in the number density and the energy density. And then we can just divide it by the number of flavors we are considering. So here it will be between all 6 neutrino flavors. And like from the beginning, I'm assuming that there is only single neutrino temperature and only single chemical potential, which can be found if you assume that the energy density in neutrinos is conserved and the number density of neutrinos is conserved. So there are only 2 processes, then it gives you the exact solution. And then we just evolve in the same way. But we can also see that in the 6 flavor equilibration, we have very similar results. We also end up with much lower electron fraction and much hotter core. So we can ask if this makes sense at all, finding such a low chemical potential for electrons with our new interaction, and that is what is on the left-hand side. So we see either the chemical potential of electrons or YE times 100. So all those values are the solutions to this equation, so the beta equilibrium equation, when we set the chemical potential of neutrinos to 0, which it has to be if we want to have those new SI and weak interaction in equilibrium. And we can see that regardless of the temperature of the electrons of the core that we would end up with, it will always lower the mu E and YE than what it was in the standard case. So standard case mu E was like 32-ish, and YE I think 43. So we always end up with the much less electron-rich core. So then, like, okay, is this our constraint? And I say, no, this is a very interesting region, which potentially, if we see something strange in the signal from the supernova neutrinos, then maybe we can pinpoint it down with an observation of the dune, or very, very, I don't know, optimistically forward physics facility, because they can also look at those mediators. We can fire the lepton number. So for us, we say that this purple region is where we would expect those drastic changes to happen, but we cannot really go back and say that it's here. Like if we see something strange in the signal, it means that it's anywhere there. So that's why then synergy with the terrestrial detectors can be very helpful. And when I say something weird can happen with this neutrino signal, the first thing is that in the previous link, we had very large peak of electron neutrinos because it was from the proton captures on electrons, electron captures on protons, mostly heavy nuclei. But now we have mostly hot neutrons and not as many electrons as before. So if the shock wave actually happens and then travels through the neutrino sphere, it is hot, so we can have more positrons, which gonna capture our neutrons, and we might have both the nu E and nu E bar bursts, and also potentially even other flavor bursts, because the other flavors rates go as temperatures, I think, to the 9. So they are very sensitive, and we increase the temperature. So that could be this kind of indication that something is happening, which would look like the lepton-number violet. Yeah, so the observable would be if we see the NUI bar burst together with the NUI burst, because we made a hot neutron star.
So detected
Detected at from the galactic supernova in the MEV range. So like, yeah. If I go back, like here in the standard case, we expect that there's only new E burst. So after the flavor conversions, it would be lower depending on the mass ordering, but we don't really expect new E bar burst or new X burst. So if we see burst in the super K, then that can be indication of the lepton-number violation. So you don't really care about the oscillation thing because they will decohere, it's very far away. So yes, so for the NUI bar, I think it's like around that is half and half NUI bar and nu X bar for both orderings. It's small difference, and for nu E, one was like I think close to the 90% or more. That the nu E will be actually nu X, and the other way for the inverted ordering, it will be similar. Yeah, nu E bar. If I see peak in nu E bar, that is, I cannot do flavor conversion with nu E. That will give me that peak. I have to do flavor conversion with nu X bar, and I don't see here X bars also having the peak. So in the non-standard scenario, that would be one potential way of telling. To infer like what is the in principle, yes. Like if you want to get the full information, if you have all flavor and then one flavor, and you assume that the X flavors are 1/4 and then you bar, then you can reconstruct it. So yes, in order to do that, you would need to have like all the detectors, looking for neutral current and charge current in both flavors. But like from the predictions now, we know that nu E bar burst so early on is not, we don't really see it and we don't expect it. So already if you see that, that is something weird. Yeah. So what is this? So this was for only the neutrino self-interactions, but now we're going to look at another work when we have neutrino non-standard interactions with quark and how that can change the supernova signal. And this is the work with an previous undergrad student, Angela, who now will be moving to the Arizona, I think, universities for her PhD and following it. So we again come back to the picture of the neutrino trapping. And now the neutrino trapping, as we see, is by the 7th interaction, so neutrino neutral current interactions with quark. So this is what we want to change. And this trapping, again, as I said before, is causing this kind of small peak before the burst. So density increases, neutrinos are escaping from the core, trapping density sets in, they are trapped, and only then shockwave releases them. So we can ask the question, how much these two peaks can change if we just change standard physics of the supernova, the electron captures here. So this process forward. So we can see if we increase or decrease the electron captures, we actually affecting both of those peaks in the same way. Like if we decrease the electron capture, we actually getting more neutrinos be able to escape. And if we are increasing them, we are getting less of them because we have more and more of them being trapped. So the standard physics changes both peaks in the same way. This is what I want you to remember. And why I'm even talking about this small peak, like we saw that this is almost 2 orders of magnitude smaller luminosity than the normal neutrinozation first peak, but there is some number of stars that are very, very close by, within 1 kiloparsec away, and that can go supernovae, or have supernovae any day now. So we, in principle, should see that small peak kind of well, even in the neutral current detectors. So if we now add our non-standard neutrino-quark interactions, so we're looking specifically for the neutral current and flavour democratic case, it will change our cross sections for the 7th process. So our standard weak factor now will be the weak factor with the NSI, which can interfere and decrease this cross section for positive epsilons. And then for the neutrino proton scattering, it will only be increasing the cross sections for the positive coupling that we are looking at here. So we can see the effects on the cross sections on this slide. In the left hand side is for 7s, and the right hand side is for the new P. So for the 7s, we have this interesting thing that the cross section can disappear for some values of the epsilon. But more interesting, I think, is the thing that for large values of the epsilon, somewhere here, we can have large non-standard physics, which mimics the standard physics, which is kind of interesting because it can hide there and we don't know about it. For then the proton, it's always increasing the cross section for the positive couplings. But this is the linear scale and that is the log scale, so there is a big difference. This is only like maybe 60% at max, and that is a large fraction of change. So what's going to happen if we add this non-standard interactions in the supernovae? So as I said before, when people look at the adding non-standard physics, we would just say that it changes the diffusion time. So the signals will be more spread or less, or maybe supernovae don't explode. So we try to do it with actual 1D simulation with the GR1D code, and we added this modified cross sections in the code to see how it changes the neutrino signal from the core. So on the left-hand side, you can see the luminosity summed over all flavors. With this solid line is the standard model case, so unchanged cross section. And then with the dashed lines are the cases when there are non-standard interactions, which will give the ratio of the non-standard versus the standard model for iron to be those values that you can see. So because in the non-standard cases, we are decreasing the cross-section for the sevens, this peak, the small peak is increasing a lot because neutrinos are becoming less and less trapped on the heavy nuclei that are there. But then if we look at the big peak, the neutrinization burst, at that point, we have the nucleons, not nuclei in the core. So it is the new peak cross section that is changed, and that is not really changed a lot for those values of epsilons. So we don't see such a drastic change here. So this is kind of nice because this cannot be confused, for example, with the changes to the electron capture, so the standard model uncertainty. But it can tell us that maybe there is NSI. Okay, so this is what I see. So we can also on the right-hand side, see how the mean nuclear mass in this pre-bound space is changing in our core. So we can then ask the question, if we modify this cross-section ratio for iron by a different amount on the downgoing slope, and the upgoing slope is the V2. So when we see the cross-section going to the hole and then up, we can see that those changes are not like 10% or so, and then there can be values of very big suppression of the cross-section because our nuclei are very, we're very increasing, especially the neutron fraction. So depending on what's the A in the core, you can have bigger effects than just naively thinking the core is just iron. Okay, so then we change the signal in the core and we want to see it, but we would best want to see it in the neutral current channels to be most sure that we see all the signal, and also there are no flavour changes that would cloud what is happening there. So we chose two detectors, which should have, for the most of the parameter space, opposite reactions to this NSI. One is Juno with the neutron-proton neutral current scattering, and on the right-hand side, it's the xenon, so it's the seventh detector with the neutrino-coherent elastic scattering. So in the new P detector, because the non-standard interaction will increase the cross-section, for this small peak, we see mostly the increase in the rate on the upper panel. But in the seventh detector, we see decrease in the rate for all the cases, no matter than here, because the xenon is heavier nuclei that we had in the suppression of our cross-section in the core, so it will still make the rate smaller. So it is nice if we now want to combine the information from these two detectors, because this can help us to reduce the supernova uncertainty, because we can have the uncertainty going up and down, but then detectors are acting in the opposite direction. We can also see here on the residuals, especially for the Juno plot, when we add, I think, 25 or 30% uncertainty in our signal, this would be this dotted gray line. So for the pre-burst, we see that it's much, much larger than just the standard uncertainty that we would add. But for the post burst, maybe not. So if we only see that part, we couldn't possibly know that there's something happening. Okay, so we did the statistical analysis where we did the combined and the separate chi-square. So we can see the combined for pairs of detectors on the left-hand side and the separate on the right-hand side. And then these blue bands are the 2 and 3 sigma regions from the coherent experiment constraints on these epsilon parameters. So in the case, if we would just have separate detectors, like some of the dark matter detectors, we can see clearly that the sensitivity goes basically to 0 once we are in this degeneracy with the standard model point right here. But if we add the Juno to it, then we see that because this detector will want to go down and this go up, something is happening clearly and we can have a nice constraint, which at this point is kind of at the same level as the terrestrial constraint. So it's kind of nice that the astro constraint can be like that. Yes. So this would be end of this. I don't know if you have questions for this part. Can you repeat the first part? Sorry, I can't hear. Agro experiment? Yes. Then what is the volume? 50. Ah, yeah, I think it's 300. So I think we looked at it because we are theorists, so we weren't, we just wanted to see the biggest detector, but in principle, we should also do the one for the smaller detector. Probably it wouldn't be as sensitive, but yes.
Yeah, because there's a delta T with like 15 years between Juno and our.
Yeah. Yeah, that's true. No, I mean, the point was just to see how to combine those types of detector, but yes, there is a large time difference between when they are supposed to come online versus that Juno is already online. Yes.
But I think your point is right. Like given what we have deployed now around the world, let's say, you know, the supernova does go off tomorrow, Juno's there.
Yeah.
Like, can we get any complementarity now?
So the Xenon and PON is online, so that could be combined. So here Darwin was 40 tons, and Xenon and PON 7 or something like that. So in principle, there would be some signal already now, but yes, that would be very interesting if we could actually not use just optimistic predictions. Yes. Should I finish or? I can talk for 10 more minutes, or I can finish now.
Minutes.
Yes, and it will be hard.
Depends if you have any questions you want.
It's fine. We can do more questions. The other part was low energy atmospheric neutrino detection, but I don't know if there are low energy people. Low energy is below 100 MeV. Okay, below 100. Yeah, then very, very fast. So one supernova, we are waiting long time. We want more. That's what DSMB is, not the one supernova galactic event, but looking at all. We can integrate over the redshift to get the flux, which would be stationary in time. The super K is looking for it. They have limits. The new bar limits are the best because that's the best detector. Maybe Dune can see it. For X flavour, the dark matter detectors put limits, but it's gonna be hard to detect. Super K said that they have excess around 2.3 sigma at neutrino 2024, but they put out a paper last year when this excess went down. But that was analysis for only the gadolinium enriched one, and this was the total one. So at the neutrino 2026, maybe there will be news. Okay, and this is just the motivation. So we want to measure the low energy atmospheric neutrinos because they are background for the DSNB search above like 20. each MeV. We know that the solar neutrinos basically are like a brick wall, but atmospheric neutrinos uncertainty will affect this detection. It will also affect the large-scale dark matter detection sensitivity, depending on what is the uncertainty for the low-energy atmospheric neutrino flux. So there has been no measurement below 100 MeV, even though the atmospheric neutrinos got the Nobel Prize for the neutrino oscillations. The low energy ones come from this pion decay chains and muon decay chains. So we have naive flavor ratio 1 to 2 to 0. Uncertainty would be how many cosmic rays comes from the solar wind and how strong it is, and also where on the Earth our detector is, because of the Earth field will affect more. That's one uncertainty. And then we can get the oscillated zenith angle average ratio of the flavors, which will be close to 1 for up to 200 MeV. Above 200, we see this effect that's either coming down or up. The one that has less time to travel will not oscillate, the other will. That's what the Nobel Prize was for. But below 200, it should be 1 to 1 to 1. So we want to then see it hopefully in the neutral current channel, which was studied and measured for the LSND detector. And this is the monoenergetic emission from the excited state of carbon 12. So from the background, we can distinguish it just looking for the line in good energy resolution detector. Juno is a very good energy resolution detector. We can then look for the charge current channel by the coincidence. So the mu E going to the nitrogen, or mu E bar going to boron. We have the prompt signal of the electron positron, and then we have the beta decay of our neutron or boron ground states. So we can distinguish here that this is new electron flavor, and in principle we can distinguish that is mu E or mu E bar because those are different light. We can also do that now for muon with triple coincidence. This has to be above 100 MeV neutrino, but we can also do this. So carbon, Juno, very good energy resolution, spatial resolution. It's already running and it's big. Then cross-section, there are some measurements from LSND and Carmen for the neutral current channel. It's very good with the elementary particle treatment of the cross-section. So again, baby prediction on the cross-section. It's good with the measurement. A neutral current channel, good mu E, good mu. It's hard to say from the data. So there are some better estimations of the cross-sections, but we want to see if we can see at least some events in Juno with this approximated cross-sections. And also, we didn't see the nu bar or nu bar one. So the measurement in Juno can give us the nu bar cross-section measurement too. Okay, so the answer, if we can see some events in Juno, is yes, we would expect around 15, if I remember, 15 events in the 85 kiloton year exposure, which can in principle give us uncertainty on the rate of 25%. If we assume that we can cut atmospheric neutral current proton scattering, which in principle we should cut because this is a gamma, this is a scattering of proton in the scintillator detector, and the same number of events in the charge current channels. Here, this is the prompt spectrum, and the background is very, very, very small here because we asking for a double or triple coincidence, so you don't expect that. So in principle, Juno could measure this low energy atmospheric neutrinos. And if we measure the mu E and mu cross sections on carbon, the charge current one we haven't been measured. Okay, that's all.